Yeah, thank you very much, Mari, for the introduction. Also, thank you to the organizers for organizing such a nice workshop and for inviting me to give a talk on this topic. So yeah, I will be discussing the gravitational wave production from the early universe, in particular, of course, from MHD turbulence and from phase transitions, and we'll make some connection also with primordial magnetic fields and how we can use gravitational wave observations for making some predictions combined with other observations of cosmological magnetic fields. So, of course, we have had already many lectures about this, so I will be very brief on the first part. But the idea is that we are trying to, of course, probe the early universe with gravitational waves. We expect that there might be some gravitational wave background if there is a process in the early universe which will be leading to the production of gravitational waves. And then we know that the frequency at which we expect this gravitational wave background to peak, it's kind of determined by the characteristic scale at which this process occurs. So if we think about phase transitions, of course, then we can try to probe the electroweak phase transition with LISA, or we can try to probe the QCD phase transition with PTA. And that, of course, you have heard by many people. So I will now be very briefly discuss what is a bit my intake of the current status of gravitational wave production from first order phase transitions. Also, like going towards the end of what Thomas has been covering in his lectures. Of course, you have already heard about first order phase transitions and their dynamics, as well as the hydrodynamics that can be induced in the primordial plasma from the nucleation and expansion of bubbles, and at the same time then from their collisions. And in particular, this will be one of the sources that we expect for gravitational waves, and I will be focusing mostly, as the title says, right, on magnetohydrodynamics. So basically, on the source of gravitational waves which are related to magnetic and velocity fields. So one of these that has been quite well studied is the production from sound waves. So since we have the collision from bubbles, and due to the spherical symmetry, we expect that initially we'll have mostly compressional motion. And therefore, if the phase transition strength is moderate, it's weak, then we expect that the fluid perturbations will also be quite small, and then we can treat this compressional motion in the linearized regime, and that's where we find then sound waves. But of course, as we start to develop any type of vertical motion in the primordial plasma, then this will lead to the production of turbulence, and we can have either just purely hydrodynamical turbulence that can be like the aftermath of these fluctuations from induced by a first order phase transition, but we can also have like fully magnetohydrodynamic turbulence, which occurs when we have not only the fluid perturbations, but we also have a primordial magnetic field present or generated during the first order phase transition. Then on one hand, this will be a kind of generating gravitational waves on its own through the anisotropic stresses I will be covering, and then on the other hand, then the magnetic field will be highly nonlinearly coupled to the fluid perturbation. So even if we would expect that initially we would have mostly compressional motion, if there is a magnetic field, that can really enhance the production of vorticity from the very beginning, and therefore lead to vertical motion, and then to the development of turbulence kind of from scratch. So of course we expect, and many of these have been covered already, like we expect many other sources of gravitational waves, and therefore if we want to make some type of an understanding of what are the underlying physics from a particular gravitational wave observation, it is quite important to have under control what are the different characteristics of the gravitational wave background from the different sources. So in this case, I'm showing kind of a state-of-the-art templates for what we expect from turbulence, and I will be covering how we are actually computing this particular gravitational wave background, and also what we expect from the sound waves. This is like some predictions from the Higgs test or some predictions from the sound shell model. So in most of the studies at the moment, since and I'll roughly mention this, the state of the art is that there is a development of sound waves, and now with the Higgs simulations, and Thomas was covering, we start to see some development of nonlinearities, but then eventually we expect that there will be like a fully developed turbulence, and in reality these are kind of the same source, it's just that they are at different stages, right? And so far we have been able to study them quite separately, but in the future actually we would like to understand, instead of just superposing these two sources at different times, to actually have the full evolution of the fluid perturbations and understand what is indeed the final the final gravitational spectrum that we expect from first order phase transition. So I will briefly cover what is the status and some comment I want to make. So of course, Thomas has already been explaining this the simulations by the SASEC Helsinki group, and then based on these simulations, which were for weak and moderate and intermediate phase transitions, then Mark developed what is now known as the sound shell model, which is what is mostly being used for the prediction of gravitational waves from sound waves. And in this model, this is kind of a semi-analytical model in which it is assumed that the gravitational wave is produced by a superposition of sound waves. So this makes a few predictions. So it allows you to compute the gravitational wave spectrum with some efficiency factor. Then it scales, I guess, quadratically with the kinetic energy density induced in the plasma, and then it's linearly proportional to the sourcing time of the process. So in general, we would expect that this gravitational wave will be produced by the sound wave regime linearly with the duration of time. And then, of course, with this prediction, we are not able to understand what happened the moments that there are nonlinearities being developed. So what is usually assumed is that this will reach some time at which the nonlinearities are being developed, and then it will saturate. But that's something that we don't completely understand at the moment, and is this connection that I like to pinpoint. That is something that with these IISER simulations we're kind of trying to see what happens in this regime as the nonlinearities start to kick in. So in most of the predictions from phase transition, especially for the sound shell model, then this is assumed to last for some duration, which is related to the eddy turnover time, which is characterized by some characteristic length scale, in this case the mean separation of the bubbles, and an inverse velocity, which can be estimated as the square root of the kinetic energy density. Some point I would like to make about this is that I will mention this in a moment, but the fluid equations, the fluid equations for a radiation-dominated fluid, they are conformally flat, so we can describe them in an expanding background by making a conformal transformation in conformal time and by rescaling the fluid variable. So any of these predictions, when we're talking about the duration, actually we should always refer to conformal time if we are making predictions based on the fluid equations. And it's an important point, and I think sometimes this it's sometimes used in cosmic time and then making a transformation, and I really think that is not the correct way to do that due to these conformal lines that I will come in a moment. So this sound shell model, as I was explaining so far, it gives us a good prediction for the weak phase transitions, but actually it's not as simple as it was previously thought. And what one finds is that we have recently been kind of revisiting this sound shell model and finding that there were like some assumptions that are not really covering are not valid at the full range of frequencies. And this is the prediction of the sound shell model initially is these gray lines, and the colored lines are kind of the new prediction after adding a contribution that was initially omitted by thinking that it was not relevant. And indeed, it is not relevant around the peak, but as you go into small frequencies, it is actually relevant and it dominates the gravitational spectrum. And this is important because even in the case where we can really trust the sound shell model, right, we expect that there's a linear production of the gravitational wave around the peak area, but then there is like a spectral shape that is relevant, especially also what Thomas was discussing about the PTA observations and how to actually try to fit this part of the spectral shape. So that is quite relevant. And at the same time, what we also find is that there is a linear growth in this part of the spectrum, but this part of the spectrum is growing quadratically. So what that means is that the source duration does not only become important for the overall amplitude, but also for the final spectral shape, because we have like two contributions which are growing at different rates, and therefore the final spectral shape would actually be quite will actually be determined by what happens during the nonlinear process, even in these cases. So then, of course, you have already seen this from Thomas' lectures. That now the simulations for strong phase transitions with the Higgs-less. Yeah, sorry. No, it does not with as h over beta. Squared instead of linear. Yeah. So it's also exactly. That's the short-lived. That's actually very similar to what we find in turbulence. It's just that then this other term usually does not appear in actually one. But I will come into that when I cover it. But sorry? Well, the knee is not the bubble size is usually around these parts, right? And then this knee is usually related to the duration. It's related to the duration, not to the. So we have an additional scale in this case, actually. In this case, they are very close, so it's difficult. But if you allow a larger separation for this duration, then actually this linear part, well, this f to the 9 actually becomes a bit more dominant for some more duration. Okay, so in these simulations, this was already presented by Thomas, but I just wanted to make the claim that actually what we find is that if we take, for example, the efficiency factor and then we compare to the sound shell model with the simulations, it agrees very well for weak transitions. But as we go into intermediate or strong phase transitions, these are the predictions by the sound shell model, we start to see that it is not predicting very well this efficiency factor. And that's a not super relevant quantity, but it's kind of just an indicator that actually has more implications than just this, that there is something else actually going on besides what we expect for a superposition of sound waves. And this can be seen if we study, for example, the kinetic energy, because what is observed in the simulations is that for weak transitions, this is roughly constant, while for intermediate and strong phase transitions, we actually start to see like a strong decay of the sourcing of gravitational waves, of the kinetic energy density. And this is, of course, not what is predicted in sound waves. So you would not have any type of nonlinearities, then this should be roughly constant and only dissipated at very late times. So this is kind of an indication that we have some nonlinearities and potentially the development of turbulence. And we start to actually observe what is its effect of this in the gravitational spectrum, because instead of having this linear growth with the source, this is for weak phase transitions. For intermediate and strong, we actually start to see a deviation, and based on these simulations, we developed kind of a theoretical model. We proposed a way to compute the gravitational spectrum and how does the unequal time correlator of the source behaves. That leads us to the result that the gravitational wave spectrum actually scales with the quadratic of with the integrated kinetic energy density squared. And this, of course, when the kinetic energy density is constant, just recovers k squared times the duration, but when it is not, actually, it follows the particular decay. And that is what then, as the kinetic energy density decays, we actually find something that starts to saturate. In these simulations, the final amplitude is still not yet saturated, but at least it's an indication of what is actually happening as you develop nonlinearities. And therefore, that our current predictions of taking just the final duration at which we expect this amplitude to happen, it's, of course, in reality, things are a bit more complicated, and we actually need to understand in the future how this actually develops because of the nonlinearities and how it gets into the final amplitude for the actual prediction. So yeah, this is kind of an indication, and it's just the part that I wanted to review about the current status of the simulations from phase transitions and from the fluid perturbations. And now I will move to some numerical studies that we have done, which are based on ones that we have developed, turbulence, how is the production of gravitational waves. So these are like some studies that we have done in the past and currently, and that's what I will be covering in the remaining of the talk. And in addition, I will be also talking about primordial magnetic fields, which in all of this scenario has kind of not been considered yet. And in general, magnetic fields can, of course, they can be produced or they can be present during these cosmological phase transitions. As I was mentioning, they are highly coupled to the plasma, so they can lead very easily to, very efficiently to the production of MHD turbulence, and therefore they can have a big impact on what are our predictions from the gravitational waves from phase transitions if they are present or produced. At the same time, if there is some seed magnetic field which is present, this can also be amplified by the turbulence induced in the plasma via a dynamo mechanism. And there are some, I won't enter in much details, but there are some ways to actually produce these magnetic fields. This was proposed by Tamai Vachaspari, in which the magnetic field could actually be produced due to the inhomogeneities of the due to misalignments of the orientation, once you have the symmetry breaking during a phase transition. So that's like a mechanism that was proposed, and therefore we kind of in general expect this magnetic field to actually be produced during these phase transitions. And at the same time, of course, we can also think if there is some type of coupling to an axion-like particle, which is effective, for example, around the QCD phase transition, then if we have a seed magnetic field, this could, for example, induce, amplify the magnetic field and lead to the production of turbulence. That I find a quite interesting mechanism to actually produce turbulence during, for example, around the QCD scale, but without requiring like a first-order phase transition. So in this case, we would directly only have the contribution from the MHD turbulence production. So, okay, there are a few more ways to produce magnetic fields that I will not enter now into detail, and I will start now discussing the production of gravitational waves and how we are computing these numerically from MHD turbulence. So we have been conducting with collaborators direct numerical simulations using the Pencil codes, which the Pencil code is an open source code with about 90 developers in a broad range of applications. And in the recent years, we implemented a module to solve for the gravitational waves, and that has attracted many applications attracted the attention for many applications in cosmology. So actually the people doing early universe physics is kind of growing. For example, Rank Kishore was yesterday talking about some simulations they have done for action inflation. And in my case, what I have been focusing is on the computations from running relativistic MHD equations, which have been adapted for the radiation-dominated era, then together with the gravitational waves equation in order to understand and predict what is the production from MHD turbulence of gravitational waves. So as I was mentioning, in general, the gravitational wave spectrum is determined by the unequal time correlators of the sources, and this, in general, due to the very large nonlinearities of these systems, they are highly nonlinear, then we usually require to conduct large-scale simulations in order to actually solve for the full nonlinearities and understand the final gravitational wave production. Also, maybe some of you are familiar with Cosmological, so at the moment we are developing a MHD module within Cosmological together with Danny Figueroa, Ken Marshall, and Antonino Midiri. So that should be ready sometime in the future. So we are describing these MHD equations by taking a continuum approximation. So we are taking an equation of state for a radiation-dominated fluid with an ultra-relativistic equation of state, and then we're solving the equations over an expanding homogeneous anisotropic background. Therefore, we have some contributions to the stress energy tensor, which of course, it was already discussed, like the stress energy tensor for a perfect fluid. That's the one that we're considering. Same time, we also have contributions from imperfect fluids, for example, from viscous stresses. And at the same time, we are also considering the contribution from electromagnetism. Therefore, as we can see, the stress energy tensor that will be in the end also sourcing gravitational waves has contributions from the velocity and from the magnetic fields. And then the equations that we are solving actually are the conservation laws for MHD, that this has already been described, and this is, of course, in the case that we don't have any interactions with the scalar field. So we are running these simulations to understand what happens after the phase transition is over. And in the limit of subrelativistic bulk flow, then we find the relativistic MHD equations, and I'm calling this relativistic because we have a relativistic equation of state, but they are still in the subrelativistic limit of bulk flow. Then this is the system in which we have some additional terms that are not present in the usual MHD. So they are slightly different. They have some relativistic contributions because of the equation of state, but they look otherwise very similar to those in a flat expanding universe, and that is because this time corresponds to conformal time, and we have rescaled the quantities. We have made a conformal transformation of the variables in order to get these expressions in which we can get rid of any explicit appearances of the scale factor, for example. Then we couple the fluid conservation laws to Maxwell equations, in which the usual assumption in MHD is to neglect the displacement current. So from Maxwell equations, we can get a direct description of the current density, and then get the induction equation for the magnetic field. And at the moment, we are preparing actually a review on these equations and extending them to the fully relativistic case that should be on the archive tomorrow or on Monday. So if you're interested, stay tuned. That's together with my PhD student, Antonio Midiri. So that will be ready. So if you want to have a look at that, you might be interested. Okay, so let me just mention, because I was talking about this conformal invariance of the fluid equation. So in order to understand that, let me just mention that this happens because if we have a Weyl transformation between two metric tensors, in this case you can think the one for an expanding universe and the one in Minkowski spacetime, which is just given by a function of the spacetime coordinates, in this case the inverse of the scale factor, then one can show that the covariant derivative of the stress energy tensor is related to the covariant derivative in the new metric tensor, together with some additional terms which can be combined after doing a conformal transformation of the stress energy tensor in a term that only depends on the trace. Therefore, if the trace of the stress energy tensor is 0, which the trace for a perfect fluid is 3 times the pressure minus the energy density, which for the case of a radiation-dominated fluid, then this becomes 0, and that allows you to then apply the equations that you would get in Minkowski spacetime to the ones in an expanding background. So, and this I wanted to mention because of the fact, for example, even for Samway's production, when we talk about this nonlinear time, and that referring to the editor over time, we have to always think that this is, of course, in conformal time, because I've sometimes seen in the literature that people kind of convert this back into cosmic time, and every intuition that we have from the MHD equations in flat spacetime, we should conformally transform that into of course a conformal time if we want to then make predictions in expanding background. So now I will. So the gravitational wave equation, you have seen this derived in many of the lectures. So in this case, we are adapting it for a radiation-dominated era, and we have the contributions from the stress energy tensor, which in this case comes from the velocity and from the magnetic fields. And then you have the details in this paper on the numerical implementation in pencil code, in case that you're interested. And I will now go into the numerical results of these simulations. So our initial setup is that we consider an initial magnetic or velocity field, which is stochastic in the sense that it follows a particular spectrum, but then it's completely random in its phase. And then we add this type of tensor structure in order to ensure that this field is divergence-free, to represent a magnetic field or to represent purely vertical velocity fields. And then these terms allows us to control the fractional helicity of the field, which I will not discuss much in detail until the very end, since it has some implications for observations. But if you are interested in that, you can come ask me at a later time. And then we initialize the magnetic field spectrum, for example, following the usual Bachelor spectrum, which is obtained from causality conditions. We expect that as we go into infinite scales, this should be always proportional to k to the 5. Below the integral scale, below the inverse of the integral scale of the magnetic field, and then for the spectrum at scales below the integral scale, then we initialize it following like the usual Kolmogorov spectrum that we usually expect for this type of turbulence. So we have a few initial parameters that we can control. So we initialize it by allowing the total energy density of the magnetic field to be an input parameter, and we always set it to be below the 10% from the BBN limit. Then we can control also the fractional helicity that can go from non-helical to fully helical, from 0 to 1. We can put the spectral peak at the different positions, which are normalized with the Hubble scale at the time of gravitational wave production. And then we can consider what is the time at which this has been generated, which is actually like a parameter that rescales out of our equation. So then we can apply it to different epochs after we have completed the equations. And that's because, of course, we're not coupling it to any scalar field dynamics, for example, in which case you can actually not do this. So these are the results from some now kind of old simulations. Well, in which with pencil code, in which we're running for in this case for a magnetic field with about 1% of the total radiation energy density at the time of production, and that is fully helical. And then here you can see the result for the gravitational spectrum, in which this is the initial magnetic spectrum, which has the usual Bachelor and Kolmogorov spectrum, also known von Karman spectrum for the full one. And from this magnetic field spectrum initially, then we compute the gravitational spectrum, and we find the usual, this is related to the Kolmogorov spectrum. But then below the peak, what we actually find is something that is linear, which is also something very similar to what Thomas was describing for the Higgs simulations. And this is kind of a characteristic K-scaling that we are finding for the first time for this, for this type of simulations, of course. And that it was also not what was initially predicted for turbulence, as people were also expecting that this should quickly go into K cube or into something slightly different than K. So, of course, we know that due to causality, eventually the gravitational spectrum should fall as K cube. And this is not what we're seeing in these simulations. So in order to understand this a bit more in detail, we ran some simulations in this paper in which we were combining different sizes of the simulation box in order to try to cover a larger range of the gravitational spectrum. And the results from the numerical simulations are the dotted red and blue, and in this case also with a few more colors. And you can see indeed that in this case we are recovering a K cube until some particular K break. And then it follows this kind of almost linear part of the spectrum, and then it finally decays into a slope which is determined by your initial slope in the magnetic field. So in this case, since we're using Kolmogorov one, then it's just related to that one. So what we find in these simulations indeed is that it follows what we were predicting in the previous simulations, but then eventually it could decay as K to the cube, which is what we're also expecting from causality. So, okay, so also what we're finding here, which is quite different from the production from sound waves, is that we are evolving as the magnetic field is present, the gravitational spectrum starts to grow, and eventually it saturates very rapidly at a time which is roughly determined by the inverse of the wave number. So it means that as time evolves, more and more modes are entering into the saturation regime. And then that's kind of, even if the magnetic field is still present, or the turbulence mechanism is still present, that it's not anymore growing. And that is different to the case for sound waves, in which case you saw that in general, it is growing linearly as long as the sound waves are present in the production mechanism. Therefore, based on this idea, since this timescale was determined by the inverse of the wave number, then, of course, as we know that the magnetic or the velocity field would take some time to start to develop turbulence and start to decay, actually, it will kind of be constant for a period of time, which is, in this case, determined by the eddy turnover time. As long as this eddy turnover time is slower than the time scale for the gravitational waves to reach saturation, we can assume that for these modes, the magnetic field is kind of constant and doesn't start to decay. And that's how we develop an analytical model that works quite well for all of these modes in which we still don't have any type of in which the gravitational waves have saturated before the magnetic field has time to start to decay. And this, in general, due to causality, usually it's like for any wave numbers above the characteristic velocity and the peak wave number. So then it means that in the limit of U star being 1, then this happens always above the peak, and if this is like subluminal, of course, this will happen at a larger range of wave numbers. So based on this idea, we developed this model in which, of course, we recover the K cube, and then we have two branches for modes which are smaller than an inverse effective duration of this process, in which this is just a constant. So this just gives us the amplitude of this of the K cube parts. And then we have an additional branch which happens at wave numbers above the inverse of this total duration, which gives us this log squared, and the log squared is because we are including expansion here. We are also finding what I was mentioning before for quadratic actually becomes log squared, also in the case of sound wave in this part of the spectrum, which for wave numbers that are sub-horizon, then this roughly becomes 1 over K squared, which then combined with this K cube, it gives us the linear K that we are finding in the simulations as well. And then eventually also we have the anisotropic stresses, which is determined by the magnetic field stresses, which is usually constant until you reach the characteristic peak wave number of the magnetic field, and then it starts to decay based on the particular initial magnetic spectrum that you had. So that's why eventually around the peak of the magnetic field spectrum, usually at 2 times that peak, you start to also observe a decay, which is combined to this linear growth, and then it starts to decay. So this model quite well explains us what we're observing in the simulations. Of course, this has the caveat that it has to be within the validity of this assumption that we're making here, which is not necessarily true for all the range of parameters, and it has only been tested in a particular range of parameters. And then also on the fact that we are for this production of gravitational waves, we are not taking into account what is the process that led to the production of turbulence. So we're just taking the part of the gravitational wave generation after the turbulence has developed and it starts to decay. So that, of course, might be relevant, and is when we need to actually make the full connection between the initial conditions that led to actually that production of turbulence, and then keep evolving and always have like an overall an overview of the full duration of the process of gravitational wave source. So this has also been by another group. This was also they were also running simulations of purely vertical hydrodynamic turbulence, so with no magnetic fields but vertical turbulence. They were also comparing to this model, and they were finding very good agreement as well. So it seems to be a model that quite well works as long as you have only purely vertical, which of course for a magnetic field that's always the case. For a velocity field, you might have in general vertical and compressional motion in the plasma. So now, of course, we have an analytical template, which again one has to keep in mind that it's valid in the range of parameters that is valid, and with the caveats of the modeling. But of course, then we can compare what would happen if we have like a turbulence process around the electroweak phase transition, and then this could be, since this could be in principle can be probed by LISA. Of course, if we look at the next generation Einstein telescope and Cosmic Explorer, this in principle could also probe like a potential period of turbulence at very large energy scales. And interestingly, we have also turbulence process around the QCD scale. This is also compatible with the PTA observations. Therefore, within the EPTA collaboration, then we were also trying to compare the data observed with this model for turbulence, and made some constraints on the turbulence model based on this result, on this analytical template that we have for the turbulence. So let me just, to finish up, talk about a little bit about primordial magnetic fields, because so far I have been considering that they are present, or they are produced during the electroweak phase transition, and they lead to the production of gravitational waves. So therefore, if we assume that this turbulence, for example, is completely produced by a magnetic field, or that the magnetic field is in equipartition with the total with the total amount of turbulence in the system, then we can make some estimates on what would be the parameters of this magnetic field, because we could know what is the total energy density in these magnetic fields and what is the spectral peak. That gives us then the strength of the magnetic field and the characteristic length scale of this magnetic field at the time of production of gravitational waves. So this, for example, it's for a range of parameters that would be compatible with LISA. We were testing what would be the corresponding magnetic field strength and coherence length scale. So this is this blob up in the left here. And then, of course, these primordial magnetic fields, they would actually be evolving through the history. They would start to decay, and then they would follow a particular decaying laws that depends on the actual details of the MHD turbulence. And actually, it's not completely well understood. It's still a very open research topic in the literature on how this would actually decay. So there are some proposals. So we have some ideas on how it should decay for non-helical fields and how it should decay for fully helical fields. And those have been also put in a bit of a doubt recently, because usually people were considering that it should follow kind of this type of decay. And recently it was proposed that, for different reasons that I'm not going to enter, but if you're interested, you can ask me, that it should actually be slightly shallower, this decay of the magnetic field strength with the characteristic length scale. So this is decaying in a process that it's known as inverse cascading, because as the magnetic field is decaying, its spectral peak is actually shifting to larger and larger scales. That is why, as the magnetic field is decaying, we actually go into larger length scales, because these are in co-moving units. So if we would actually only have the expansion of the universe, this would just be a fixed point. So you have to also think that this evolution is really only because of the effect of MHD turbulence. Therefore, these magnetic fields could actually evolve. In this case, for the non-helical fields, should follow these green lines. In the case of fully helical, should follow these purple lines until they could reach Rabi recombination, and then at that time they would kind of be they might be present then in the cosmic voids of our universe, for example, where we expect them to actually be almost not affected. And actually, there are some observations by the Fermi collaboration from distant places which have been putting some lower bounds on very large large scale intergalactic magnetic fields, which is like around here. This is kind of a conservative estimate on on what should be the strength of these magnetic fields, of these intermagnetic fields, which are in principle might be present in the cosmic voids of the large scale structure. So then, of course, we can try to make a connection between the magnetic field that should be present around the electroweak phase transition, in this case, for a production of gravitational waves compatible with this magnetic field. Then this might decay following, for example, if it's completely non-helical, one of these decays, and then it can be above what is expected from the Fermi observations to explain at least this as the potential origin of these intergalactic magnetic fields. At the same time, we also have some upper bounds from some Faraday rotation measurements from CMB constraints also up here. And this is also quite promising because now with the Cherenkov telescope array, this is what we expect to have the sensitivity. So it might be in the coming years, actually, we might actually have some type of observation from this. At the same time, we also have an upper bound, as I was mentioning, from Big Bang nucleosynthesis. So we can try to at least make a type of multi-messenger approach to study these primordial magnetic fields in which we're combining gravitational wave observations, gamma ray observations, as well as CMB and so on. So yes, something similar can also be done with PTA, of course, and then that's what we did in this paper. And then we were considering that it follows like completely what is expected for a non-helical field. And then this is the lower bound from Fermi observations that I was mentioning before. And this is what we expect is this point when it intersects with the recombination line. That is what we would expect to actually be at these cosmic voids. And at the same time, this is quite interesting. This was proposed by Pogosian and Jedamsik. And then in this paper with Silvia Galli, they were actually doing some data analysis combining different observations. That if there is such a magnetic field which is present around the CMB, then this would actually lead to a larger value of the Hubble rate at present time than the one that is usually taken from CMB. So that has been proposed also as a way to. It does not solve the Hubble tension, but it can slightly alleviate it if there is a strong magnetic field which is present. This is kind of debated in the community. Some people are not completely convinced about this argument, but it's a quite interesting way to also think about these magnetic fields. And with this, I go into my conclusions. So in general, I have velocity and magnetic fields in the early universe, and they can significantly contribute to the stochastic gravitational wave background of cosmological origin via sound waves and MHD turbulence in general. In general, we also required to perform high resolution numerical simulations, which for the phase transition have been mostly conducted by the SASE Helsinki group, and also for the Higgs simulations, they have been conducted mostly by the DESI group. And for vortical turbulence, these have been mostly done with the pencil code. So also, as I was mentioning at the very beginning, since the stochastic gravitational wave background is expected to be a superposition of many sources, and some of these are also completely under control, or we might expect to even have unknown sources, it is extremely important to actually have a very good understanding and an accurate characterization of the different sources if we want to be able to extract any clear information from the early universe physics. The interplay at the moment between sound waves or compressional motion, if you want to consider this also in the nonlinear regime, and the development of turbulence, so of vertical motion in the plasma and eventually turbulence, is at the moment not completely well understood, because we have the regime of simulations for the phase transition, the regimes of simulations for turbulence, but we want to kind of make a connection in the future, as this plays an important role on the relative amplitude of both sources of gravitational waves. And in the end, we don't want to consider this as two sources, but actually like the final gravitational wave that we expect from fluid perturbations in the primordial plasma. So there are some ongoing studies of phase transitions also with pencil codes. And so LISA, PTA, and next generation ground-based detectors, they can be used through their potential probing of these phase transitions. They can also try to be used to probe the origin of the magnetic fields which are indirectly observed in the larger scales of our universe, which is an open question if these are actually from cosmological origin or from some astrophysical origin. And yeah, so this is what I was mentioning. Then gamma ray observations then can constrain these intergalactic magnetic fields. This provides us a way to to study these primordial magnetic fields in a kind of a multi-messenger approach. So yeah, I think this says thank you in Kannada. I'm not sure, but yeah, thank you very much for your attention.
Comments? Yes.
In the beginning, you talked about this probability, the possibility to produce magnetic fields from the scalar field.
Yes.
So the scalar field is the SU2 doublet here, or
is what? Sorry. Yes. Yeah. I mean, this is this is from the Higgs field, from the doublet. So you can have it if you have gradients of the if you have misalignments of the orientation, even though they are in the same expectation value. You have different patches, right, when you break symmetry, and that can actually lead to. It's a pity that Tamma is not here because he could address that much better than me, but yeah. Yeah, that's a difficult. So for the moment, okay, for the moment we're just in, but yeah, eventually that could be the idea to have like with the scalar fields in general. That could be, of course, the very good to have. But yeah, at the moment we're just implementing the hydrodynamic module and some also now some applications with magnetic fields. So it can be studied, and once that is kind of tested and all, then we can start also putting some interactions with different fields, and then of course the SU2 cross U1 eventually. Yeah.
Yes.
This one or this one? Yeah. Of the spectrum? Yes. So yeah, this spectrum is what we expect from causality. So any field below its integral, so like at scales larger than its integral scale that are divergence free should follow this type of spectrum. So that's the motivation for this part. And then this is what we expect from Kolmogorov turbulence. This is what we expect once that the turbulence has developed. This is quite well understood for hydrodynamic turbulence. It's true that for MHD turbulence, this might not be exactly like this, but at the moment we're only seeing that it has like a small impact on the slope. If this would be instead of -2/3, well, I need to convert it because I usually work -5/3 instead of 2, but yeah. Yeah. Yeah, so I mean that magnetic field, once that it starts actually once that it starts interacting with the full plasma, then one expects that it starts to develop this type of spectrum eventually. So it will maintain kind of the scale invariant part, right? But then at the frequencies where you actually have some type of interaction with the primordial plasma, it will start to develop this.
The primordial magnetic field is not feeling that it follow some power law, then what would happen?
Well, that's what we have studied here. Actually, we are not considering the case from inflation because in that case, right, this is because of causality. So if you are actually generating it during inflation, then you don't have kind of this condition, and then you have the usual scale invariant spectrum. Okay. So in this case, this is kind of assuming that it comes from a phase transition or from some causal process.
Okay.
So if it could come from inflation, these initial conditions should slightly be changed.
So the second question, so you have, when you are solving this hydrodynamic equation, so this is essentially background plus some fluctuations. So what about the metric perturbation component in that dynamics?
Yes, in here we are completely ignoring any type of feedback. So we're assuming that all the perturbations in the metric tensor are much smaller than the background.
Okay.
The moment you start going into very large perturbations, of course, one needs to go into the full GR MHD and understand in that regime.
Yes, please.
So I have a very naive question. So when some magnetic field exists before the, let's say, electric phase transition, for instance, U1Y magnetic field, then does it affect the electric phase transition itself? Like, for instance, if you have a, let's say, stronger U1Y field, then I was wondering if, the bubble profile itself is affected, right? So it's not spherically symmetric anymore. So yeah, does it affect like a gravitational wave spectrum from the first order phase transition?
Yeah, that's a good point. I completely agree that if you have like a strong magnetic field from the beginning, that's of course going to interact with your fields, right, during the electrowave phase transition, and that might change the dynamics of the phase transition itself. But yeah, that's something that I cannot comment much more about it, right? But I agree. I don't think that it has been really much studied or much understood because it's kind of a complicated problem.
Okay.
Yeah.
Thank you.
Other questions? Well, if not, let us thank Alberto.